we introduce the energy method to derive this second order constant coefficient ODE. Okay, so actually this time I will show you how to use the potential method to derive actually the same ODE. Okay, so here we have actually an inductor and a capacitor in series. So actually the circuit is as simple as this. Okay, so we only have two nodes and we only have and we also have one as the ground. So we only have a single variable V here. Okay, so we can also assume the current to be clockwise. Okay, you may assume it to be counterclockwise if you want. It doesn't really matter. So okay, so maybe we can draw it explicitly like for the inductor L, the current is from bottom to top, and for the capacitor here, for the capacitor on the right side, the current is from top to bottom. Okay, so we may, so as I mentioned earlier, so I usually divide the voltage according to the direction of the current. So as much as for the capacitor, the current is from top to bottom. Okay, we define this one to be V, this one to be plus, this one to be minus, and this one is V, this one is 0. So okay, the potential difference across the capacitor should be V. Okay, similarly, the I going through the L is from bottom to top. So I will let this one to be plus, this one to be minus. Okay, so this is 0, this is V. 0 minus V will be negative V for the potential difference across the inductor. This is a little bit we need to pay attention to. Okay, so if you still remember for the capacitor and inductor, each of them has an equation. For the capacitor, it is nothing but I equals C dV dt. C dV dt. Yeah, because we already make it like V, rather than VC, VL, something like that. So I equals C dV dt. And then for the inductor, okay, V, okay, this V should be negative V here, okay, because yeah, we define the direction like this. Okay, so the voltage across this inductor in this setup will be negative V equals L di dt. Okay, so we have these two ODE. Okay, so we would like to solve it, and yeah, so it doesn't really matter if you like to eliminate I or eliminate V. Okay, yeah, both of them are okay. So in this case, I'd like to, let's say, we try to eliminate I. Okay, 就是 eliminate I 就是消去嘛，就是有两个，就是 I and V. Okay, I and V are also unknown function that we would like to find. Okay, so and then we have two ODEs here. So we may eliminate one so that it makes it like a single equation with only one unknown function. So here we like to eliminate I because this is a V. Okay, so sharing by them. Yeah, so to eliminate I, it is very simple. So for the second equation, negative V will be nothing but L times d dt, and then we put in the I here, which is C dV dt. C dV dt. We just put this one to here. Okay, so C is a constant, so it is nothing but L times C, and then it becomes the second derivative of V with respect to time. Okay, so in this case, we can also divide LC on both sides, and then we try to arrange the terms. So it turns out to be the second derivative of V with respect to time plus 1 over LC times V equals 0. So LC and LC cancel. So we have this term, and then we move this one to the other side, and then divide by LC. So it becomes 1 over LC times V. Okay, and then the sum to be 0. Okay, so this is it. And then you may say, oh, this is different from the previous one. Okay, here we have Q. We have Q here. Okay, but as much as this is a linear system, okay, this is a linear system or linear circuit, okay. So for any unknown variable, you can simply exchange it to arbitrary variable. Let's say it will be, with some step you can also write it as a d2v dt2 plus I, and then 1 over LC I equals 0. Okay, so the coefficient will be the same. What we only change is the variable. And actually we can also change it to something like this. Okay, so as much as this is a linear system or linear circuit, we may be able to do that. We can do that. So we only change the unknown function here. Okay, actually I can show you why we can go from here to the first one to the second one. Let's say okay, so actually we can take the derivative on both sides. So we have a third derivative with respect to v, and then plus LC times dv dt. Okay, so we just take derivative on both sides, and then we can just multiply it by c, so it becomes c d3v dt2 d3 dt3, okay, dt3 here, and then plus 1 over LC times c dv dt. Okay, c dv dt. Okay, so don't forget that we have I equals c dv dt at the beginning. Okay, which means this is nothing but I. Okay, so this is nothing but I, and then 1 over LC, and then something like this. Okay, so for the third derivative, we can just put the c inside and then separate the third derivative into a second derivative and a single derivative. So it turns out to be something like d2 dt2 and then c dv dt. Okay, we just put the c inside. Okay, but leaving one derivative there. So this one is also an I, so it turns out to be dti dt2 plus 1 over LCI. Okay, something like this. So we may be able to go from the first one to the second one. And for this one, actually we can easily do it from the third one to the second one. Okay, you just take the derivative on both sides, and then take the derivative on both sides, and then make use of I equals dq dt. Okay, and then it becomes the second one. So this is just a simple demonstration, show you that for a linear circuit you can freely to change the unknown function. Okay, they will all satisfy the same constant coefficient ODE. Okay, so this is how we can simply derive this equation using the potential method. Okay, so actually we can have some analogy to the mechanical systems, because most of you are civil engineering students. You should be familiar with the mechanical system, I think. So let's see. Okay, suppose we have a mass connected to a spring with a coefficient to be k, okay, something like this. Okay, we can also try to derive the second order ODE like this. So according to the Hooke's law, which is f equals negative kx. Okay, so the kx, the x can be like this is the x-axis. Okay, so if there is no forces acting on it, we may define this position to be a 0. Okay, and maybe you can grab it to the right side. Okay, so become a positive x, and then there will be a force pointing to the negative side. So we have a negative side here. Okay, we have a negative side here. Yeah, because it is related to the direction. Okay, you grab this mass to the right side, the force will point to the left side. You push it to the left side, the force will be acting towards the right side. Okay, so actually this is the Hooke's law. Okay, this is the Hooke's law. Hooke's law. Okay, actually also according to the Newton's second law of motion, F equals ma. Yeah, but we will not use ma. Okay, we will not use the acceleration. Rather than that, we will use m d2x dt2. Okay, because we know the acceleration is the derivative of the velocity and also the second derivative of the displacement. Okay, so this is a is nothing but d2x dt2, or you can also write it as the first derivative of the velocity. Okay, so this is an acceleration, the velocity and the displacement. Okay, so we make use of this because we have x here, so we should leave it at x there. So yeah, so here by looking at these two parts, and then we can just divide m on both sides. We have a d2x dt2 plus k over mx. Okay, so this is also a second order constant coefficient ODE. Okay, although the only difference between this one and the LC oscillation is that we have 1 over LC here. Here we have a k over m here. So, but actually they are somehow the same. Second order constant coefficient ODE. So many of the equation can be shared by just changing something like LC to be m over k, something like that. Okay, so here we can quickly see how we can solve this one. Yeah, using the mathematic work we have learned previously. So this is the second derivative. We change it to s squared and then plus k over m, and then times 1 equals 0. So s will be plus or minus j and then square root of k over m. Okay, so pay attention that I used to write j to be the negative, the square root of -1, rather than using I. Okay, So here we will have this omega to be square root of k over m, or we can actually write it as plus or minus j omega. So this will be the oscillation frequency. So similarly for this one, we can also write it as s squared plus 1 over LC equals 0. So s will be plus or minus j times square root of 1 over LC. So here the oscillation frequency will be 1 over LC, and in that case, S will become plus or minus j omega. So both of them becomes S equals plus or minus j omega, and then yeah. But the only difference is that this lateral frequency is square root of 1 over LC, and this one is a square root of k over m. K over m. Okay, so according to what we have learned before, so as much as we have this solution, these roots for the characteristic equation, the solution x of t will be like a times cosine of omega t plus b sine omega t. Okay, if you still remember. If you don't remember, you try to study the slide before. Okay, so already talk about that before. Okay, but in the textbook we will usually write it as something like let's say this is a capital X or whatever variable you like, and then write it as a cosine of omega t plus phi. Okay, so this is what we learned in your high school trigonometry， 就是高中三角的时候，其实会花蛮多时间去教你把这个同一个频率就是同一个频率的 sin 跟 cosine， 然后变成一个同一个频率的 sin 跟 cosine。这里两个幅度 a 跟 b，a 乘以 cosine 跟 b 乘以 sin， 到这里就会变成 x， 一个正幅总的正幅，跟一个相位。Okay, so it will probably like this x will be square root of a squared plus b squared, if you still remember, and then this phi will be like negative arctangent of b over a. Okay, or it can be negative arctangent of b over a, or pi minus tangent b over a, depends on which quadrant it is in， 就是跟象限有关，因为 arctangent 的话只有两个象限，看你怎么定义。一般的话我们会用第4跟第1象限，但是万一它在第2、第3象限的话，你要加个派，让1/4 map 到2、3象限，明白我意思吗？就是如果 a 是负数的话，那你就要加这个派。如果是 a 是正数的话，那就是用上面那个没有加派的那一个因为它要变成一个类似是它要变成一个是 r 乘以 cosine phi cosine omega t 减去 b sine of phi and then sine of omega t， 它就会变成像这样如果你这里不是 b 这里是 r， 这里是 r， 或者应该是 x 不是 r， x okay, something like this. Okay， 就是变成cosine 减 sin， 它就会变成 cosine 加Okay, so in the textbook it just show you that okay, from this one, from this second order constant coefficient ODE, the solution will be like this. Okay, so we just change the form. Okay, here we have a x of t equals x times cosine omega t plus phi. Okay, so here we just write it as a q equals capital Q. This is the magnitude. This is the amplitude. This is the 振幅. Okay, times cosine omega t plus phi. Okay, so this is the oscillation. And okay, according to this, we can just plug in here so that the current will be the first derivative of the charge with respect to time. Okay, so the first derivative becomes q times cosine. The derivative of the cosine becomes negative sine. So negative q sine omega t plus phi. And then for the chain rule, this part take the derivative with respect to time becomes another omega. Okay, so another omega goes to here. So this omega is due to the chain rule. Chain rule. Okay, so this is the current. The current. Okay, something like this. Okay, so as much as it has solved the Q and also the I here. Okay, so remember how the textbook derived the equation. Okay, so it is actually according to this one, UE equals Q squared over 2C and UB equals Li squared over E. Okay, half of Li squared and half of Q squared over C. So now we already solved Q and I. We have already solved Q and I. So we can just plug in those two equations into here and here to write the expression of UE and UB. Okay, so UE becomes Q squared over 2C, and then okay, so I just write it here again. So Q equals capital Q cosine omega t plus phi, and then I equals negative omega Q sine omega t plus phi in the previous page. So we put this here. Okay, so we have Q, capital Q square over 2C, and then cosine square of this stuff. Okay, so this is the energy, the electrical energy stored in the E field. And for the B field, for the magnetic energy, it is nothing but half of Li square, So we can plug this I to here. So negative square becomes positive. So here we still have positive energy. And we have omega Q. So we have a omega square Q square, and then over 2C. Sorry, it should be like half of Li square is omega square Q square, and then sine square of this omega t plus phi. Okay, so this one is a little bit different with this one, but we know that omega square is 1 over LC. Omega is square root of 1 over LC. Omega square is 1 over LC. So here it becomes 1 half L times 1 over LC, and then times Q square sine of this stuff. Okay, so L and L cancel, so becomes Q square over 2C, and then sine square of this stuff. Okay, so here we can observe something, okay, according to this UE and UB. So the first observation is that the maximum values of UE and UB are both Q square over 2C. Okay, it just want to show that these two terms are the same. And at any instant, the sum of UE and UB is equal to Q square over 2C. Yeah, because when you add them together, these two are the common factor, and then the remaining stuff becomes cosine square of this, and then plus sine square of this. Okay, so in trigonometry, you know that's a sine square of theta plus cosine square of theta. Is actually 1. Okay, so when we add them together, when we add UE and UB together, it becomes Q square over 2C. Okay, and the third one is when UE is maximum, UB is 0, and then conversely, because it adds up to be this one. Okay, and then the maximum value can be this one when cosine is plus or negative 1. Okay, when cosine is plus or negative 1, UE takes this value, and then which is equal to this one. So which means UB should be 0 at the time, and then vice versa. Okay, so this is trivial. Okay, so according to this result, it actually verified that the conservation of energy, conservation of energy 就是能量守恒嘛，就是我们当时写了一个就是 du dt 等于0， du dt 等于0，那这个是一个常数嘛，所以就是 du dt 等于0啊。Something like this, okay. So yeah, so this is like half of the q squared over 2c, okay, in between, okay, because yeah, this cosine square is like cosine square of something is like half of 1 plus cosine of 2 times this stuff, okay, and then sine square will be 1 minus this stuff, okay. So it is like a shifted version of the cosine, okay. Originally, if it is a cosine, it should be ranged from -1 to 1, or a sine will be ranging from -1 to 1. But in this case, this is like -1 to 1, and then plus 1 will become 0 to 2. Divide by 2 will become 0 to 1. Okay, so this sine wave is like shifted between 0 and 1 times q squared over 2c. 就是大概是这意思。Okay, so far any questions? 有没有问题？Okay, so now we have a sample problem. Yeah. So it says a 1.5 microfarad capacitor is charged to 57 volt. The charging battery is then disconnected, and a 12 millihenry coil is connected in series with the capacitor, so that LC oscillation occurred. What is the potential difference VL across the inductor as a function of time? Okay, so actually we have d2q dt2 plus 1 over LCQ equals 0. And in that case, we can just make it like Q equals capital Q cosine omega t. Originally, we should have plus phi, but we can just let phi to be 0. For some cases, we can make this assumption, yeah, because it is just the time shift. Okay, if we don't care about the time, okay, the absolute time, okay, then yeah, we can arbitrarily set a phi to be any value. So if we set it to 0, of course it will be easiest case, because we don't need to add something else. Okay, adding something else will be more complicated. Okay, we just assume phi to be 0. So in this case, Q will be C times V. Q will become C times V as we have before. So C is 1.5 microfarad, 1.5 times 10 to the negative 6, and then times 57 volts. Okay, so this is 8.55 times 10 to the negative 5th coulomb. Okay, so this is the maximum charge. Or at the beginning, the charge which is stored in the capacitor at the very beginning. Okay, so it asks you VL. So VL will becomes L di dt, and actually I will be dq dt. I should be dq dt. Okay, so this is nothing but L times the second derivative of small q dt2. Okay, so we need to take the derivative of q, okay, which is this one. Okay, so of course you can take it one by one, but actually, okay, we can do it quicker. So which is like for the derivative, q doesn't change, so we put this q here, and then cosine, the first derivative becomes negative sine, negative side, derivative again becomes negative cosine. So we have a negative cosine of omega t. And then the last step is we still have the chain rule. Okay, for the chain rule, we need to derivative this part and then square it because we take the second derivative. So for the first derivative, 1 omega comes out, and then for the second derivative, another omega comes out again. So it becomes omega squared. Okay, so it becomes negative LQ, and then omega squared is nothing but 1 over LC, and then cosine omega t. Yeah. Okay, so we can actually cancel this L with this L, so it becomes a negative Q over C cosine of omega t. And this Q over C is nothing but V. Okay, so it becomes negative V cosine omega t. So this is nothing but negative 57 volt, and then cosine omega. Okay, what is omega? Omega will be 1 over square root of LC. So square root of LC, L is 12 times 10 to the negative third power. This is L, and then C is 1.5 times 10 to the negative 6. Okay, so this is negative 57 cosine. This is 7,500 T. Okay, so actually this one is in radian. Okay, radian per second. This is a radian. This is the angular frequency. Omega is angular frequency. Okay, so the unit, the SI unit of the omega of the angular frequency will be radian per second. Okay, radian per second, not hertz. Hertz is the normal frequency. Okay, so the SI unit will be V. The SI unit will be V because this is VL of time. Okay, so this is VLT across the inductor as a function of time. Okay, so it's also a cosine function. Yeah, if we assume this Q to be like that. Okay, so for the second question, okay, what is the maximum rate dIdt max as reach the current I change in the circuit? Okay, so here we need to find dIdt and then take its maximum. So first we recall Q equals capital Q cosine omega t. Okay, so I is actually dq dt, which is negative q omega sine of omega t. Okay, and then we need to take the derivative of I. So di dt is nothing but negative q omega square cosine omega t. Okay, so here we would like to take the maximum value of this one, which is di dt max. Di dt max will be q omega square. Yeah, because we can have cosine omega t to be 1. Okay, so this is the condition. When cosine of omega equals to 1. dIdt to take its maximum value, so which is nothing but Q times 1 over LC, and then we can plug in all the numbers. So Q from here is 8.55 times 10 to negative 5th, and then 1 over LC. 1 over LC. Yeah, 1 over LC, we already know that it is it is 1 over LC should be 7,500 square, okay, because this is 1 over square root of LC. This is 1 over square root of LC is 7,500. So 1 over LC should be 7,500 square. And this will be nothing but 4,800 A per S. Yeah, the SI unit will be like this is A, this is A, this is S. So this is A per S, 4,800 ampere per second. Okay, so this is first sample problem. Then here we would like to talk about the damped oscillation. Damped oscillation 这个叫做阻尼的震荡阻尼 damped oscillation. Yeah, so here the textbook also use the power method, okay, or I should say the energy method. The energy method. Okay, so up to here it is still the total energy. U to be UV plus UE, and then this is the energy stored in the inductor, half of Li squared, and then this is the energy stored in the capacitor, Q squared over 2C. And then we don't store energy in this resistor. Okay, so for this damped oscillation in the RLC circuit, so the only difference is that we include this resistor here. Okay, so it becomes an RLC circuit. Okay, but when we consider the total energy, we don't store energy in the resistor. Okay, the resistor only consume energy. 它只会消耗那个功率的或者能量的。它不会储存能量。那 L 的话会储存能量 ，C 也会储存能量。它们 LC 的话就不会消耗能量但我是说这种理想的状态之下，如果你真的买一个电容或电感回来的话，它肯定有一些内电阻，就会消耗能量的。所以真实状态底下的话，这种 LC 电路的话，其实是不存在，这个只是数学上会存在，那它总是会消耗掉。那如果真的电路上要做一些震荡器的话，我们需要有一些其他的源头灌注一些能量给它，让它保持着震荡。如果你单纯给一个 LC 电路一些能量，它不会永远的震荡下去。Okay, so let's go back to here. Okay, so here, so what is the role? 它这个电阻有什么角色 ？Okay, so the role here is that here we don't have conservation of energy. Rather than that, the energy will be consumed by the resistor. So here it says, however, the total energy decreases as energy is transferred to thermal energy. 它就会变成一些热，就是消耗掉。Okay, the rate of the transfer is du dt. Okay, this is actually the power. Okay, take the derivative of the energy with respect to time will be the power. Okay, so the power will be negative I square R. Originally I square R, but here to demonstrate it is a decrease. Okay, decrease in total energy. So we have a negative sign here. So du dt, which is P, would be negative I square R. So here what we do here is we also take the derivative here. Okay, so we will get the similar stuff as before, or similar terms as before, which is this term and this term will be correspond to these two terms, the derivative of these two terms. Okay, and then the remaining stuff is we will get this term. So maybe I can just show you a bit. Okay, how could we come up with this one? Okay, so the du dt, will becomes okay, so Li, okay, L times I and then di dt, okay, just follow the previous derivation, okay, and then plus, and then here we have Q over C, and then dq dt, okay, so this is nothing but negative I square R, okay. So we can use some change of variable. Change of variable means we would like to replace I by dq dt. So it turns out to be for the first one, Li becomes dq dt. So we have dq dt, and then di dt becomes a second derivative of q, and then plus Q over C is okay, and then we have a dq dt, and then why not moving it to the left side? So we have a plus R times dq dt square equals 0. So in this case, we can just divide L and dq dt on both sides. So L and dq dt cancel with this one and this one. Okay, so we only have the first term to be here. And then for the second one, dq dt and dq dt cancel, so becomes Q over LC, which is the last term. Okay, and then finally here, dq dt and dq dt cancel, so we only have one dq dt here, and then we have R over L to be the second term. So this is actually like this. Yeah, but here we notice that we have this term. Yeah, so it becomes a complete second order constant coefficient ODE. Okay, so it becomes more complicated. Yeah, and actually in the textbook it only tells you that okay, the solution to this second order constant coefficient ODE, the solution will be like that. Okay, like this. And then also the omega prime will be the original omega square minus this small term, and then take the square root. So it will be slightly smaller than the omega. Yeah, because this is a positive value minus a small value. So and then take the square root. So it must be slightly smaller than this one, slightly smaller than the original omega, where the omega is the same, or 1 over square root of LC. Okay, so the textbook is just like that. It just it doesn't tell you why it be like that. Yeah, but of course we can also derive the equation with the potential method, like this. So actually, so we may do some derivation first. So here we have VC to be like this. This is VR like this, and then VL like this, and then the current is clockwise, just as what we done before. Okay. So in that case, I equals, so we have for the first one, so for the inductor, for the L will be VL to be LDI dt, okay, and then for the resistor, it is nothing but VR equals R times I, okay, V equals IR. Yeah, but I would like to put the unknown variable I, unknown function I at the end. And then also, and then for the VC, for the capacitor, we have I equals CdV C dt. Okay. Yeah. So we have this 1, 2, 3 equation. And then also we can use the KVL to write VL plus VR plus VC equals 0. Okay. So in this case, what we can do is, we try to plug in this one to here, this one to here, and yeah, that one is not. We cannot plug in this one to here yet. Yeah, but we try to plug in the first two. So we have a L di dt, and then plus R times I plus VC to be 0. Okay, and now we try to take the derivative. We try to take the derivative and multiply by C. Okay, we try to take the derivative and then also multiply by C for this equation. So it becomes a LC and then the second derivative of I, and then plus RC and then d I dt, and then plus C dVC dt. Okay, so here we notice why we need to do this stuff. Okay, because this one will become this one, so which is nothing but an I. So here we have a LC d2I dt2 plus RC di dt plus I. Okay, so in this one we only have this I, this I, this I. Okay, and then we can actually divide LC on both sides, so it becomes a d2I dt2 plus R over L di dt, and then plus 1 over LC I to be 0. Okay, you may say that the equation is Q, so as I mentioned, you can just change I to be Q, so you can also have d2Q dt2 plus R over L dQ dt, and then plus 1 over LC Q to be 0. So this one is actually the same as this one, R over L 1 over LC, R over L 1 over LC, second derivative, first derivative, original function. Okay, so actually up to this point we have already derived the same equation using the potential method rather than the energy method. Okay, so maybe let's have a 10